So here we'll start off by talking about characteristic subgroups. So H is characteristic in a group G. Written as H char G. So this char is in place of the other types of symbols we usually use. If sigma of H equals H for all automorphisms sigma. So it's worth pointing out, if H was normal in G, then G HG inverse is equal to H for all G in G, which, based upon our last discussion, means that the map I've been calling phi of G of H equals H for all inner automorphisms. So the inner automorphisms fix the normal subgroups. And your subgroup is normal if and only if you are fixed by every inner automorphism. So being characteristic is a stronger property. It's saying that you're fixed as a set by every automorphism. And again, by the same distinction, this is as a set, not pointwise. So the automorphism will permute the elements of H, but it permutes them among themselves. It's like saying that somehow you're making students in each classroom, in a given classroom, change seats, but you're not letting anyone leave the classroom. These two facts together clearly tell you that if H is a characteristic subgroup, then it's definitely a normal subgroup. Why? Because, well, if you're fixed by every automorphism, then you're fixed by the inner automorphisms, which means you're fixed by conjugation. So if you satisfy this definition, then you satisfy the definition of being normal. So this is a stronger property because it has more requirements. One of the other facts about characteristic subgroups is the following. Suppose you have a group of order n. Let D be a divisor of n. Suppose there's a unique subgroup of order D. Then H is characteristic in G. Well, why should this be true? Well, just let sigma be an automorphism of G. Then sigma of H is a subgroup of G. And so this is a fact about group homomorphisms. Group homomorphisms send subgroups to subgroups. But a fact about group isomorphisms is that they send subgroups of a given order to subgroups of the same order. So the image of H has to have the same size. Oh, but there's only one subgroup of that size, so sigma of H better be H. Sigma was an arbitrary automorphism, so this is true for every automorphism. Thus, H is characteristic in G. Finally, the other property the book mentions about characteristic subgroups, it has to do with normality conditions. If K is characteristic in H and H is normal in G, then K is normal in G. So it's a fact that if K is normal in H and H is normal in G, it's not necessarily the case that K is normal in G. The reason why is because the definition of normality depends on the two groups. Saying K is normal in H just says that when you conjugate K by elements of H, you get K back. And when you conjugate H by elements of G, you get H back. But it's possible, and there are counterexamples with those assumptions, that when you conjugate K by elements of G, you might not get K back. So the point here is that with this stronger assumption, we actually managed to get the conclusion we would have liked with normal subgroups. And so it's kind of nice. And so the proof is not too challenging. What are we given? Well, we're given the fact that these two facts, and what do we want to show? Well, we want to conjugate G by K. K by G. So this is what we want. For all G in the group G. Well, what can we do? What is this conjugation? It's this inner automorphism applied to K. So equivalently, we want to show that when you apply this inner automorphism to K, you get K. Well, since H is normal in G, conjugation is an automorphism. In particular, we already have established this, that we have this homomorphism from G into the automorphism group of H, where phi of G is exactly this conjugation operation. And so in this, with this hypothesis, we have this homomorphism. And so for every G, phi sub G is an automorphism of H. Oh, but K is a characteristic subgroup of H, which means that K is fixed as a set by every automorphism of H. So in particular, phi of G of K has to be K, which is what we wanted to show. And so the point is, when K is normal in H, we can't conclude anything about K being normal in G because we know nothing about conjugation of K by elements of G. But when K is characteristic in H, we can get the conclusion we want because conjugation by elements in G is actually an automorphism of H. Of course, they don't discuss this in the book, but you could ask yourself, well, we've got this new thing called being characteristic. Well, what happens if I strengthen both hypotheses? Can I strengthen the conclusion? Is the property of being characteristic a transitive property, or a transitive relation? And it turns out this is true, and I might assign it as a homework problem. If K is characteristic in H and H is characteristic in G, then K is characteristic in G. So this forms a partial order with respect to this relation, which means that it is transitive, it is reflexive in the sense that every group is characteristic inside itself, and it is antisymmetric. If two subgroups are characteristic inside each other, they're the same group. Now let's look at some examples. Let's consider the automorphism group of Z mod NZ. So what are you looking for? You're looking for an isomorphism with Z mod NZ to itself. And of course, any homomorphism from Z mod NZ to itself is determined by what it does to 1. What do I mean by this? Because then sigma of n is really just the nth power of sigma to the 1. So you just have to figure out where to send 1 to. And if you send 1 to anything other than a generator, then it's not an isomorphism. Why? Because the image becomes a proper subgroup rather than the whole group. In order to be an isomorphism, it has to be surjective. And so what do you need? Well, you need generators. And what are the generators of Z mod NZ? Well, the generators correspond to integers a, such that a is between 0 and n, and the greatest common divisor of a and n is 1. In other words, the group of units as a set. So for example, if I wanted to look at Z mod 12Z, sigma of 1 would have to either be 1, 5, 7, or 11. Because in any other option, you would end up getting an element that generates a proper subgroup. But these 5 elements generate the whole group. Now, the remarkable fact is that actually it is isomorphic to the group of units under multiplication. So remember, Z mod NZ is a group under addition. So we're working with it as a group under addition. The automorphisms end up giving you multiplication, which is kind of funny, but that's just the way it is. So how do we see that? Well, what are we identifying the automorphism with? We're identifying with its image of 1. Why? Because we already just determined that sigma of n is just the nth power. Equivalently, it's just n times sigma of 1 because you're talking about an additive abelian group. And we already just mentioned the only homomorphisms that actually give rise to automorphisms are cases where sigma of 1 is in this set. So we actually do have a function from the automorphism group of Z mod NZ to this set. And you can see that it must be surjective. If you manage to pick one of these choices, you actually do in fact get a automorphism. So all you need to show is that it's injective and that it's a homomorphism. Well, how do you show it's a homomorphism? I guess given one of these choices, let's let sigma I of 1 be I. Well, what's sigma I of sigma of j of 1? Well, it's sigma I of j, which by definition of automorphism is just j times sigma I of 1, just j times I, which is sigma of ij, 1. And you can prove that when I and j are coprime to n, their product is also coprime to n, modulo n. So here I'm working with modular arithmetic. And so you do in fact get the group homomorphism property. So not only does this map exist, but it preserves the multiplication. So it sends composition of automorphisms to multiplication of integers coprime to n. So the only thing left to really check is that we're injective. Well, let's check its injectivity. Well, what's sigma of 1? It's got to be the identity in Z mod NZ, the group of units. But what is that? It's just 1. You have an automorphism from Z mod NZ to itself, and it sends 1 to 1. It is the identity function. So, congratulations, the kernel is trivial, and therefore we have our isomorphism. And so there are some interesting examples to consider. The book states these without proof, because usually it's proven in other parts of the textbook, so we'll see if we'll get to those parts in this course or if they pop up in the ring theory sections. I certainly do remember learning them as an undergrad, but one of them is that this multiplicative group of units is cyclic of order p minus 1. That proof actually takes a little bit of effort, but it is true. In particular, Z mod PZ is actually a field, so it's the non-zero units of the field actually happen to form a cyclic group in that case. Note here we're assuming it's an odd prime. On the other hand, if you're working with a power of 2, you end up with Z mod 2Z times Z mod 2 to the n minus 2Z. Here, of course, there's some restriction, n has to be at least 3. So these are things that take some arguing, which I won't present in this course, but it's worth pointing out some stuff is known. Man, that gets kind of interesting, isn't it? The next interesting example is you have an abelian group. We're going to use V for some reason. That becomes clear in a moment. And we fix a prime P. We're going to write the group additively, and the claim is that every element has order P. And you can prove that V is actually a vector space over the field Z mod PZ. Why? Because, it's additive already, and multiplying could correspond to repeated addition, and you've got the extra criterion you need that since P is congruent to 0, when you're doing this scalar multiplication, it behaves the way it's supposed to. This is equivalent to multiplying by the 0 vector. 0 scalar, you do get the 0 vector back. In this case, the automorphism group is actually the general linear group of n by n matrices over this field, where V has to have size p to the n. So you get a vector space. It has to have, assuming this set was finite, it has to be finite dimensional, so it has to be p to the n for some n. Your automorphism group ends up being matrices. So you actually get linear algebra out of automorphisms. And now we get to my favorite, the automorphism group of the symmetric group. It's quite interesting. When n is not 6, you actually get Sn. Now remember, any group G embeds as a subgroup into the automorphism group by this whole, Z mod ZG, right? By this whole inner automorphism thing, and the center of the symmetric group is always trivial, and so you do get this connection. But a weird thing happens when n equals 6. It's actually not the symmetric group. And when n equals 6, Sn has index 2. There's a non-trivial outer automorphism. And I will eventually detail exactly one example of such an automorphism. And it actually relies on the observation I made before. So remember, one observation we made about conjugacy classes was that the conjugacy classes of S6, if you look at the conjugates of an adjacent transposition like 1, 2, there were 15 conjugates. And this had order 2. Now remember, any automorphism is going to preserve the conjugacy classes, and it's going to preserve the orders of elements. On the other hand, the conjugacy class of this permutation also has 15 conjugates, and this also has order 2. And we remember in conjugation in the symmetric group, conjugacy classes are determined by their cycle types. And in particular, any automorphism that actually sends conjugacy classes to themselves is going to be one of these inner automorphisms. So the only way there's a non-trivial automorphism is if you have one that induces a permutation of the conjugacy classes that's non-trivial. In particular, we need something that replaces one of these adjacent transpositions to one of these triple transpositions. And it turns out such an outer automorphism actually exists, and it's kind of cool. And it involves group actions to construct it, but we're not quite there yet. But when we get there, we construct this outer automorphism. You see that it can't come from a conjugation map, because the only way it could come from a conjugation map is by sending this to another adjacent transposition. And you'll see that this map actually sends one of these permutations to one of these permutations. And so there's an actual non-trivial outer automorphism.